Hi, it's Mrs. Mays, and we are going to look at the nucleus today. So we talked earlier about what is matter made of, and Ernest Rutherford came up with some ideas about what atoms are made of because of radioactivity. So in his time, radioactivity was just discovered by Henri Becquerel and Marie and Pierre Curie. But he was using three different types of radiation. He noticed that there was alpha particles, which were large and heavy and slow moving. There were beta particles, which were much smaller and faster moving. And then there was such a thing as gamma rays. The important difference here is that alpha particles had a positive charge to them, so when they passed through electrically charged plates, they would get deflected towards the negative end. And then beta particles were negatively charged, so of course they get deflected towards the positive end of the plate. And then gamma rays were not particles at all. They were beams of pure energy, and because they didn't have a charge, they simply passed straight on through. So these three different types of radiation were discovered and described by Ernest Rutherford after other scientists had discovered that radiation existed in the first place. Then he was able to Rutherford was able to describe what those radioactive particles were like. Then he used these particles in an experiment. Rutherford shot alpha particles at a thin sheet of gold foil, and that's why we call this the gold foil experiment. This experiment was so shocking that even Rutherford didn't quite believe it at first. He was watching to see how would the particles pass through or would they be deflected. Here's what he found.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position, behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. we look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom by comparison is very big, so it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Okay, so let's see if Rutherford's idea really holds up. In fact, Rutherford was shocked by these results. He said, it's as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Well, a shell is like a bullet, so if you fire a really big bullet at a piece of tissue paper, you expect it to just go on through, right? Well, his conclusion was that there must be a lot of empty space in the atom, and there must be a central positive charge. So he took Dalton's idea and modified it to say there's a positive charge in the center of the atom, and then the electrons would be orbiting around it in sort of going outside of it, right? But then here's the problem. He couldn't explain what happened then. In the solar system model, if you have two things that are attracted for one another, like a positive charge in the middle and a negative charge out here, well, eventually their force, the attractive force between them, brings them together, and, well, that would kind of be the end of things, right? So Rutherford had a lot of other things to learn about the atom, but knowing that the nucleus was dense and positively charged was a huge stride forward in understanding how the atom works.